I want to ask you to think about the following scenario as precisely as possible. You have just landed on Mars. The mission went exactly as planned. The spacecraft performed flawlessly. The transit took 210 days. You landed in Jezero Crater, near the remnants of an ancient river delta, at the site that was selected years ago for its scientific interests and its relatively flat terrain. You stepped out of the lander, stood on red iron oxide soil under a butterscotch sky, with atmospheric pressure at your feet equivalent to the atmospheric pressure on Earth at 40 kilometers of altitude, and you did it. You are the first human being to stand on another planet. Now, the question that nobody in the popular narrative about Mars missions wants to answer directly: how do you get home? Not in the abstract, not in the mission planning document, in the specific physical situation you are now in, on Mars, with the equipment you brought, the physiology you arrived with after 210 days in microgravity, the propellant situation on the surface, and the orbital mechanics that determine when you can leave. How do you get home? The answer, when you work through it precisely, is that you might not be able to. Not because the rocket broke, not because of a medical emergency, but because the combination of physical and biological constraints on a round trip to Mars is severe enough that the return journey, even under optimal conditions, may exceed what the human body can survive in a functional state. I want to build this argument carefully because the individual pieces are each known and each is discussed in the technical literature, but the full combination of them, presented honestly and simultaneously, is almost never laid out in popular accounts. The popular accounts describe the challenges of getting to Mars, the challenges of surviving on Mars, and note that the return is a similar challenge. What they do not do is show you the full compounding of those challenges, the way each one adds to the others, until the total picture is clear. Let me start at the moment of landing, because what your body has already been through by the time you touch Martian soil is essential context for everything that follows. You left Earth 210 days ago. From the moment your spacecraft left low Earth orbit, you entered a physiological environment that the human body was not designed for and has no evolutionary preparation for. There is no gravity. There is no wind. There is no open sky. There is no variation in temperature between morning and evening, no seasonal light cycle, no rain, no soil, no organic complexity of any kind in your immediate environment. There's a metal box, a crew of your colleagues, and the tasks of the mission. In microgravity, the skeleton is no longer loaded by the body's weight. On Earth, every step you take compresses the bones of your spine, hips, and legs with forces several times your body weight. Every moment you stand, your postural muscles work against gravity to maintain your position. This continuous mechanical loading is what keeps bone mineral density at functional levels. Bone is a living tissue. It responds to the forces applied to it. Osteoblasts, the cells that build bone, are stimulated by mechanical stress. Osteoclasts, the cells that break down bone, are suppressed by mechanical loading. In zero gravity, the mechanical stimulus disappears and the balance shifts toward net bone resorption. The numbers are precise and well documented from International Space Station data. In the lumbar spine, astronauts lose approximately 0.9% of bone mineral density per month. In the femoral neck, the narrow section of bone connecting the femoral head to the femoral shaft, and the site most commonly fractured in falls involving osteoporosis, the loss is approximately 1.5% per month. In the distal femur and proximal tibia, load-bearing bones of the knee joint, losses of 1 to 1.5% per month have been measured. After 7 months, the cumulative loss in the femoral neck is approximately 10%. 10% of femoral neck bone mineral density represents a fracture risk increase that is clinically significant in elderly patients with osteoporosis. In a young, healthy astronaut, The absolute fracture risk is lower, but the reduction in bone strength is real and measurable. The specific concern for a Mars mission is not that your bones will break while you are on Mars, where the gravity is lower and the mechanical loads are correspondingly reduced. The concern is what happens when you return to Earth and begin loading those weakened bones again. The exercise countermeasures on ISS include approximately 2 hours per day on resistance devices, specifically the Advanced Resistive Exercise Device, which simulates weight-bearing exercises including squats and deadlifts, and aerobic equipment including a cycle ergometer and a treadmill with a harness system that pulls the astronaut toward the treadmill surface to simulate gravity. These countermeasures reduce bone loss by approximately 40 to 50% compared to no exercise. They do not prevent it. After 6 months on ISS, astronauts still typically land with measurable bone density deficits that require months of rehabilitation to partially recover. The pharmacological countermeasures available include bisphosphonates, drugs that inhibit osteoclast activity and reduce the rate of bone resorption. Several bisphosphonates have been studied in space contexts, with results showing modest additional benefit on top of exercise countermeasures, but not complete prevention of bone loss. The research is ongoing, and better pharmacological countermeasures may be developed, but no currently available agent eliminates bone loss in microgravity. Muscle atrophy proceeds through different mechanisms, but at similarly significant rates. The postural muscles, the soleus and gastrocnemius in the calves, the muscles of the lower back, the quadriceps and hamstrings of the thighs, all lose mass at rates of approximately 3 to 5% per month without countermeasures. With the exercise countermeasures available on ISS, the loss is approximately 1 to 2% per month. After 7 months, the total muscle volume loss in the lower body may be 15 to 20%, even with maximum exercise. The muscle loss compounds the bone loss in a specific way. The muscles are not just motor actuators, they also apply mechanical loads to the bones during contraction. When muscle mass is reduced, the peak forces applied to bones during movement are also reduced. This means the bone strengthening effect of exercise is partially negated by the reduced muscle mass that limits the forces that exercise generates. The two forms of deconditioning feed each other in a negative cycle that exercise countermeasures can only partially interrupt. Your cardiovascular system has also adapted to the microgravity environment in ways that are relevant to the return journey. On Earth, the heart pumps approximately 5 liters of blood per minute at rest against the hydrostatic pressure of the blood column in the body. In microgravity, the fluid distribution in the body shifts upward. Blood that would normally pool in the lower body redistributes toward the chest and head. The heart's preload, the volume of blood filling the ventricles before each beat, is higher in microgravity than in Earth gravity. The heart responds by reducing its size. The left ventricle, which pumps blood to the body, decreases in mass by approximately 10% over 6 months. The fluid shift also triggers the kidneys to excrete excess fluid, reducing total blood volume by approximately 10% over the first few weeks in space. The body has recalibrated its fluid balance for the microgravity environment. When you return to gravity, the blood redistributes back toward the lower body, and the smaller heart must suddenly manage a higher hydrostatic load with a reduced blood volume. This is the mechanism underlying orthostatic intolerance, the inability to maintain blood pressure when standing upright after spaceflight. In the hours and days after landing from a 6-month ISS mission, approximately 60% of astronauts are unable to stand for 10 minutes without experiencing significant drops in blood pressure, lightheadedness, and sometimes syncope. They must be assisted when leaving the Soyuz capsule after landing. Most recover within days to weeks. After 7 months in microgravity, followed by 500 days on Mars at 38% gravity, followed by another 7 months in microgravity, you are returning to Earth after approximately 21 months in below Earth gravity out of a total mission of approximately 30 months. The cardiovascular deconditioning at the end of this mission is not simply 7 months of ISS equivalent deconditioning. It is the accumulated effect of the transit, the surface stay, and the return transit, each with its own partial recovery and partial redecline. The specific concern for Earth re-entry is that the spacecraft decelerates at 3 to 4 Earth gravities. This is the equivalent of standing under 3 to 4 times your body weight for approximately 8 to 12 minutes. For a cardiovascular system that has been partially adapted to 38 gravity for 2 years, this is an extraordinary demand. The risk of cardiovascular compromise during re-entry is a specific and quantified concern in Mars mission, medical planning, and current countermeasures, which were designed for 6-month ISS missions, may not be adequate for a 3-year Mars mission. On Mars, you have 38% of Earth's surface gravity. This is better than 0 gravity for your physiology. Mars's gravity will begin to reload your skeleton and your postural muscles, but it is not enough to fully reverse the deconditioning from 7 months of microgravity. Research on the effects of partial gravity on bone and muscle is limited because no human being has yet lived in sustained partial gravity other than the brief and fragmented data from Apollo lunar surface days, which lasted at most 3 days. The specific rate of recovery or continued loss in 38G for 500 days is unknown and is one of the most important physiological unknowns in Mars mission planning. What we know from ISS data is that the recovery of bone mineral density in full Earth gravity after a 6-month mission takes approximately 2 to 3 years, and recovery may be incomplete. Some astronauts show persistent deficits years after return. The recovery of bone mineral density in 38G during a 500-day surface stay is unknown. Models suggest that partial recovery would occur at a rate proportional to the gravitational loading, so perhaps 38% of the recovery rate in full gravity. But this is extrapolation, not measured data. The specific problem for the return journey is this. You need to be able to perform physically demanding work on Mars for 500 days, then survive another transit in microgravity, and then re-enter and land on Earth in 1 full gravity, with a body that has been in low or 0 gravity for a total of approximately 21 months. The physical demands of return include, at minimum, monitoring the propellant plant, preparing the ascent vehicle, executing the ascent burn sequence, rendezvous with the Earth return vehicle in Mars orbit, and surviving the trans-Earth transit. Let me now describe the radiation that has accumulated in your body during the transit to Mars, because it compounds the bone and muscle situation in ways that are not simply additive. The transit to Mars in interplanetary space, outside the protection of Earth's magnetosphere and the heliosphere's partial shielding, exposes you to galactic cosmic rays at levels that have no equivalent in any environment accessible to humans on Earth. Earth's magnetic field deflects most charged particles below approximately a giga-electron volt of energy. The heliosphere's magnetic field reduces the flux of galactic cosmic rays below approximately 100 mega-electron volts. On Earth, the atmosphere absorbs most of what reaches it. On a spacecraft in interplanetary space, none of these protections exist. Galactic cosmic rays include protons, helium nuclei, and heavier ions up to iron nuclei, accelerated in the remnants of supernovae and other violent astrophysical processes throughout the galaxy. They arrive isotropically from all directions, with energy spanning many orders of magnitude. The most biologically damaging are the heavy ions, specifically nuclei heavier than helium, called HZE particles for high Z and high energy. Iron nuclei at typical galactic cosmic ray energies have an atomic number of 26 and travel at significant fractions of the speed of light. When a heavy ion traverses tissue, it deposits energy along a narrow cylindrical track by ionizing the atoms it passes through. The linear energy transfer, the energy deposited per unit length of track, is proportional to the square of the atomic number. An iron nucleus deposits approximately 676 times more energy per unit length than a proton of the same velocity. This dense ionization track creates a cylinder of damage that includes direct DNA strand breaks, damage to the surrounding cellular infrastructure, and oxidative stress extending several micrometers beyond the particle's path. The biological consequences of this damage pattern are qualitatively different from those of X-rays or gamma rays, which produce sparse, isolated ionization events that the cell's repair machinery handles relatively efficiently. HZE particles create damage clusters that are much harder to repair correctly. The relative biological effectiveness, the ratio of HZE damage to X-ray damage at the same absorbed dose, ranges from approximately 2 to 5 for most endpoints and up to 20 or higher for specific chromosomal damage endpoints. The transit dose depends on the specific heliocentric conditions during the mission, particularly the phase of the solar cycle. Near solar maximum, the solar wind is denser and faster, which partially shields the inner solar system from lower energy galactic cosmic rays by producing a more effective magnetic barrier. Near solar minimum, the shielding is less effective and the galactic cosmic ray flux is higher. The MSL Curiosity rover's radiation assessment detector measured the radiation dose during the Mars Science Laboratory transit in 2011 to 2012, providing the first direct measurement of the interplanetary radiation environment on a Mars trajectory. The measured dose was approximately 1.8 millisieverts per day, or approximately 330 millisieverts during the 180-day transit. Subsequent modeling using solar activity projections gives transit dose estimates ranging from approximately 150 millisieverts during solar maximum to approximately 300 millisieverts during solar minimum for a typical 210-day transit. The dose is not evenly distributed in time or particle type. Solar energetic particle events, sudden increases in energetic particles from solar flares or coronal mass ejections, can deliver doses of tens to hundreds of millisieverts in hours to days. These events are partially predictable with advance warning of hours, allowing crew to shelter in a more shielded region of the spacecraft, but cannot be entirely avoided. The Mars surface dose depends on the Martian atmosphere's shielding effect and the locally produced secondary particles. The Martian atmosphere has a surface pressure of approximately 600 pascals, varying with season and altitude, equivalent to approximately 16 grams per square centimeter of material. This is modest shielding, equivalent to approximately 6 centimeters of water. It stops low-energy particles, but is mostly transparent to the high-energy galactic cosmic rays. The RAD instrument on Curiosity measured the surface dose rate at approximately 0.21 millisieverts per day, or approximately 76 millisieverts per year. In 500 days on the surface, you accumulate approximately 104 millisieverts. The return transit adds approximately 150 to 300 millisieverts, depending on solar activity. Total mission dose, from the transit to Mars, the surface day, and the return transit, you accumulate approximately 400 to 700 millisieverts, with the most likely value under average solar conditions, approximately 550 millisieverts. NASA's current career dose limit for astronauts was revised in 2022 to use a risk-informed approach based on an effective dose limit of 600 millisieverts for a career, regardless of age and sex, with the goal of limiting the increased lifetime risk of exposure-induced death from cancer to 3% above baseline. A complete Mars round trip delivers a dose that is close to or exceeds this career limit in a single mission. For the most radiation-sensitive individuals, specifically younger women whose bone marrow is more radiosensitive, the mission dose may significantly exceed the career limit. The cancer risk, significant as it is not the most operationally relevant effect during the mission itself. The cognitive effects of galactic cosmic rays, particularly the HZE component, are more immediately concerning for mission success. Multiple studies at NASA's Space Radiation Laboratory at Brookhaven National Laboratory have exposed mice and rats to beams of accelerated iron nuclei at doses comparable to a Mars transit. The results are consistent and disturbing. Animals exposed to iron nucleus beams at doses of 10 to 25 centigrade, comparable to the HZE component of a Mars transit dose, show statistically significant deficits in spatial learning, measured by performance in maze navigation tasks, where the animal must remember the location of a hidden platform. Animals exposed to iron nuclei show slower learning rates and more errors than controls. Memory consolidation, measured by performance in fear conditioning tasks, where the animal must remember an association between a context and an aversive stimulus. Iron-irradiated animals show reduced consolidation of these memories. Executive function, measured by tasks requiring behavioral flexibility and the ability to switch strategies when the rules of the task change. Iron-irradiated animals are slower to switch strategies and make more perseveration errors. Anxiety-related behavior, measured by open field and elevated plus maze tasks. Iron-irradiated animals show increased anxiety-like behavior, spending more time in protected areas and less time in open areas. The mechanisms include direct ionization of neurons, inflammatory cascades mediated by activated microglia and astrocytes in the central nervous system, reductions in dendritic spine density that reduce the number of synaptic connections, and alterations in hippocampal neurogenesis, the production of new neurons in the hippocampus that is important for memory function. The specific cognitive functions affected, spatial memory, executive function, and behavioral flexibility, are precisely the functions required to operate a spacecraft, navigate to the ascent vehicle, execute launch procedures, manage equipment malfunctions, and maintain crew cohesion during stressful events. They are not peripheral abilities. Whether the dose-response relationships in rodents translate quantitatively to humans is unknown. Human brains have more neurons, more redundancy, and different architectural features than rodent brains. The extrapolation from mouse to human is never simple for neurological endpoints, but the direction of the findings, that high-energy, heavy ion radiation damages the neural substrates of cognition, is not in dispute. The specific magnitude of the effect in humans is the unknown. By the time you are ready to depart Mars for the return journey, you have been exposed to radiation that, in animal models, produces significant and measurable cognitive impairment. The specific cognitive functions most affected are precisely the ones you need to operate a spacecraft, make decisions under uncertainty, and manage emergencies. The return transit requires you to be cognitively functional for its entire duration. The radiation history of the mission makes this uncertain in a way that cannot be resolved without actually doing the mission. Ready to change how you see the world? There are 12 principles in my book that address exactly this kind of reasoning. What the physical constraints on human existence actually are, and what they tell us about our place in the universe. Get your copy of 12 Principles for Understanding the Fabric of Reality at realityprinciples.com. Now let me take you to the propellant problem, which is the most immediate and most concrete barrier to the return journey, and where the binary nature of the return commitment is most stark. The return trip from Mars to Earth requires a specific sequence of propulsive maneuvers. First, the ascent from the Martian surface to Mars orbit requires a delta V of approximately 4 kilometers per second, depending on the target orbit altitude and the specific launch trajectory. The Martian gravity well is weaker than Earth's, with a surface gravitational acceleration of 3.72 meters per second squared compared to Earth's 9.81, but the ascent still requires a substantial propellant mass. Second, the trans-Earth injection burn from Mars orbit onto a return trajectory requires approximately 1 to 2 kilometers per second, depending on the specific trajectory and the degree to which the mission exploits gravitational resonances. Third, the Earth arrival, whether through direct atmospheric entry or Earth orbit rendezvous with a waiting vehicle, requires additional maneuvering delta V. Total delta V for the return sequence from the Martian surface to Earth, approximately 5 to 8 kilometers per second, depending on the specific mission architecture. The propellant for these maneuvers cannot be brought from Earth. The mass of propellant required is enormous. For a Starship-class return vehicle, approximately 1,200 tons of liquid methane and liquid oxygen. Launching 1,200 tons of propellant from Earth, landing it on Mars, and having it available for the return trip would require an extraordinarily large number of cargo flights and would dominate the mission's launch mass budget in a way that makes the mission impractical. Instead, the return propellant must be manufactured on Mars. The chemical reactions required are known. The Sabatier reaction converts carbon dioxide and hydrogen to methane and water. CO2 plus 4H2 yields CH4 plus 2H2O. Electrolysis of the water produces oxygen and hydrogen. 2H2O yields 2H2 plus O2. The oxygen becomes the oxidizer. The methane becomes the fuel. The hydrogen from the water electrolysis is recycled through the Sabatier reactor. The net process takes Martian CO2 and imported or locally sourced hydrogen and produces liquid methane and liquid oxygen. The Martian atmosphere is 95, 3% CO2 at a surface pressure of approximately 600 pascals. The CO2 is abundant and accessible. The hydrogen is the limiting reagent. It can either be imported from Earth on cargo missions in the form of water or hydrogen gas, or it can be extracted from Martian subsurface water ice. Mars has extensive confirmed water ice deposits. The Phoenix lander found water ice at depths of a few centimeters in the northern polar region in 2008. The Mars Reconnaissance Orbiter has detected subsurface water ice at mid-latitudes using radar sounding. The Mars Express Orbiter's Marsis radar found evidence of a subglacial lake beneath the south polar ice cap. Accessing these deposits requires drilling equipment and extraction infrastructure. The specific engineering required to mine water ice from Martian permafrost and feed it into a propellant plant has never been demonstrated, but there are no fundamental physical barriers to doing it. The MOXIE experiment on the Perseverance rover has demonstrated the oxygen production part of the process at small scale. MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment, is a device the size of a car battery that uses a solid oxide electrolyzer to split CO2 into oxygen and carbon monoxide. It is operated intermittently during Perseverance's mission and has produced a total of approximately 122 grams of oxygen over multiple runs as of 2023, with a peak production rate of approximately 12 grams per hour, or about 288 grams per day. The return propellant requirement of 1,200 tons corresponds, in terms of oxygen alone, to approximately 900 tons at MOXIE's demonstrated peak production rate of 288 grams per day, producing 900 tons of oxygen, would take approximately 8.5 million days, or approximately 23,000 years. The required scale-up from demonstrated performance to mission requirement is a factor of approximately 8 million in production rate. This factor of 8 million is not a reason to conclude that the propellant production is impossible. Engineering scale-up of chemical processes is routine in industrial chemistry. The specific scale-up from MOXIE to a mission-capable plant involves designing a larger solid oxide electrolyzer, engineering the thermal management for a larger device operating in the Martian environment, and integrating the oxygen production with the methane production from the Sabatier reaction. None of these steps involves new chemistry or new physics. They are engineering challenges. But the engineering challenges are substantial, and the timeline is unforgiving. The propellant plant must be delivered to Mars on unmanned cargo missions that precede the crewed landing by months to years. It must land on Mars without damage. It must be deployed and operate autonomously without human maintenance in an environment that has never been the site of sustained human engineering. It must achieve the required production rate of approximately 2 tons per day over approximately 18 months. It must fill the return vehicle's propellant tanks to the required level, and this must be verified before the crew commits to the surface landing. The verification problem is critical. Mars is too far for real-time remote operation. At the communication delay of 4 to 24 minutes each way, any fault that requires an operator intervention takes 8 to 48 minutes minimum to address. Faults that require parts, repairs, or hardware changes cannot be addressed from Earth at all. The plant must either operate without faults or fail in ways that its autonomous fault detection and correction systems can handle. The decision to commit the crew to the surface landing, made when the lander separates from the Earth return vehicle in Mars orbit, is the most consequential single decision in the entire mission. At that moment, the propellant tanks on the surface are either full or they are not. If they are not full, the crew will not be able to return. There is no option to abort after landing on the surface. There is no option to fill the remaining propellant from Earth. The crew lands knowing that the propellant situation is what it is and the return depends on it. This is the nature of the propellant commitment, and it is unlike any previous human spaceflight mission. On the Moon, if the ascent engine had failed, the crew would have been stranded on a world where death would come in hours from oxygen depletion, not in weeks or months from starvation. On a Mars mission, a propellant plant failure discovered after landing might allow the crew to survive on the surface for months or years, while Mission Control attempts to devise a solution which cannot involve rescue on any relevant timescale. The crew would have time to know exactly what was happening to them, to understand precisely the nature and degree of their predicament, with no ability to change it. Ready to change how you see the world? The principle that connects all of these specific barriers is one of the deepest in the physics of complex systems, the compounding of irreversible commitments. This is at the heart of what I explore in my book. Get 12 principles for understanding the fabric of reality at realityprinciples.com. Let me now take you to the orbital mechanics, because the return launch window is not a matter of preference. It is determined by the positions of Earth and Mars in their orbits, and it is one of the most unforgiving constraints in the entire mission. Mars orbits the Sun at a mean distance of 1.52 astronomical units in an orbital period of 686.97 days, or approximately 1.88 Earth years. Earth orbits at 1 astronomical units in 365.25 days. Because the two planets orbit at different angular rates, Earth completes slightly more than 2 orbits, while Mars completes slightly more than 1, and the relative geometry of the two planets repeats approximately every 780 days, or about 26 months. This is the synodic period of Mars. Let me derive why the return window constraint is so severe. because the numbers involved are precise and the physical origin is the Hohmann transfer orbit geometry. The most fuel-efficient trajectory between two planets on circular orbits is the Hohmann transfer, an elliptical path that is tangent to the inner planet's orbit at its perihelion and tangent to the outer planet's orbit at its aphelion. For Earth to Mars, a Hohmann transfer orbit has a semi-major axis of 1.26 astronomical units, a perihelion at 1 AU, Earth's orbit, and an aphelion at 1.52 AU, Mars's orbit. The transfer takes approximately 259 days. For the Hohmann transfer to work, the target planet must be at the aphelion of the transfer orbit at the moment of arrival, and the departure must be timed accordingly. This requires the planets to be in a specific angular alignment at departure. The geometry repeats every 780 days. Real missions use trajectories that are not perfect Hohmann transfers. Because Mars's orbit is elliptical with eccentricity 0.093, and the actual positions of the planets at any given time differ from the idealized circular orbit case. Mission planners compute the actual optimal trajectory numerically for specific launch dates. The result is a launch window of approximately 20 to 60 days every 26 months, during which the required delta V is within the spacecraft's capability. Outside this window, the required delta V increases rapidly, and missions launched significantly outside the window would require prohibitively large propellant masses. The critical constraint for the return mission is that the return launch window opens approximately 500 days after the crew's arrival on Mars. This is not a coincidence. The conjunction class mission profile, which is the standard reference mission architecture for a crewed Mars mission because it minimizes total propellant requirements, explicitly plans for a surface stay of approximately 500 days to take advantage of the return launch window that opens after the Earth and Mars have moved to the correct relative positions. 500 days is approximately 16 months. If the crew arrives in the northern hemisphere spring of any given year, they will be on Mars through 2 northern hemisphere winters before they can depart. During this time, the Martian seasons cycle through, Martian dust storms potentially develop, and the crew must maintain all systems in continuous operation with no resupply possible from Earth. The tolerance on the launch window departure date is narrow. A launch that is 1 month early or 1 month late requires significantly more delta V from the ascent vehicle and the trans-Earth injection stage. A launch that is 2 months early or late may exceed the propellant available. The crew cannot decide to leave early because they are ready or because conditions are deteriorating. They must wait for the window. If the return launch vehicle fails and is not repaired before the window closes, the crew must wait an additional 26 months for the next window. The total surface stay extends to over 40 months. The additional radiation dose is approximately 200 millisieverts. The additional physiological deconditioning in partial gravity continues. The psychological burden of a mission extension that exceeds the planned duration by over 2 years, with no communication in real time and no possibility of rescue, is a factor that has no analog in any planned or executed human mission. The specific technical failure modes that could prevent the crew from using the return window include failure of the propellant production plant to produce the required propellant, structural failure of the ascent vehicle, failure of the ascent vehicle propulsion or avionics, failure of the life support systems in the habitat requiring early evacuation that cannot be executed until the return window, and medical emergencies that incapacitate the crew before they can execute the ascent. The probability of each of these failures is unknown with any precision because none of the relevant systems has been operated on Mars. We can estimate component level failure rates from terrestrial or Earth orbit data, but the Martian environment, with its dust storms, UV radiation, temperature swings of 100 degrees Celsius between day and night, and atmospheric composition, introduces failure modes that may not be present in the component level data. The specific point I want to make about the return window is its binary character. Unlike the transit to Mars, where abort trajectories exist for some of the outbound journey, the surface stay has no abort option. Once the crew is on the surface, the only way back is through the ascent vehicle and the return trajectory, which opens at a specific time and for a specific duration. This binary character makes the return from Mars qualitatively different from any previous human spaceflight mission, where some form of abort or early return was available at almost all mission phases. The principle that connects this to the deepest questions about the nature of human existence in the universe is this: we are not a universal species. We evolved for one specific environment, and every departure from that environment costs us physiologically and cognitively in ways that accumulate and do not fully reverse. 12 of the principles that I believe most fundamentally change how you see the fabric of reality are in my book, Ready to Change How You See the World. Get 12 principles for understanding the fabric of reality at realityprinciples.com. Let me now address something that I think is systematically understated in public discussions of Mars missions: the psychological dimension of the return journey and the specific way that psychology interacts with the physical constraints I have described. 500 days on Mars, in a habitat the size of a small house, with a crew of 4 to 6 people, with no possibility of leaving and no possibility of rescue. Communication with Earth delayed by 4 to 24 minutes each way, making real-time conversation impossible. No fresh food, no outdoor environment accessible without a spacesuit, no unstructured time in a natural setting. Every day organized around mission tasks and survival requirements. The psychological literature on isolated, confined, and extreme environments is the best data we have for what this does to human beings. Antarctic winter overstations isolate small groups for 8 to 14 months in conditions that are physically harsh, but that have Earth gravity, regular communication with the outside world at zero delay, and the knowledge that rescue is possible within months if needed. These environments produce documented psychological effects that are well characterized at this point. The most consistent finding is that crew members in isolated, confined environments typically show a deterioration in mood, cognitive performance, and interpersonal relationships that accelerates in the second half of the mission. Researchers have termed the third quarter phenomenon the predictable dip in performance and mood that occurs when the mission is approximately 3/4 complete. The mechanism is believed to involve both cumulative fatigue and the psychological experience of being close to the end without being there yet, which creates a specific frustration that is different from the challenge of the mission's middle phases. In the Mars context, the third quarter phenomenon would occur approximately 375 days into the surface day, or roughly 12 months in, when the crew knows the return window is still more than 4 months away. The combination of a known proximate end, the return window, that is still far enough away to be psychologically distant, with the accumulated physical and cognitive effects of radiation, partial gravity, and closed habitat, creates a specific risk profile for crew cohesion and individual psychological stability. The interpersonal dynamics of a small isolated crew over a 500-day period are also relevant. Studies of Antarctic winter overcrews and submarine crews consistently find that interpersonal conflicts are one of the most significant stressors in isolated, confined environments. In a crew of 4 to 6 people, personal incompatibilities that are minor irritants in normal life become magnified over months of forced proximity. There is no option to take a walk outside, or to spend the weekend with different people, or to seek physical distance from a crew member with whom you are in conflict. Conflicts must be resolved within the crew without the option of external mediation in real time, while simultaneously maintaining the operational demands of the mission. The Mars mission adds specific stressors not present in Antarctic or submarine environments. The communication delay makes psychological support from Earth qualitatively different. A crew member in distress cannot have a real-time conversation with a counselor or family member. They must send a message and wait at minimum 8 minutes for a response. And the response arrives without the emotional tone, facial expression, or immediacy that makes human emotional support effective. This is not a minor operational detail. It is a fundamental limitation on the quality of the psychological support that can be provided. The medical emergencies that are possible on a 500-day Mars surface mission include trauma from falls or equipment accidents during EVAs, acute illness including appendicitis or cardiac events, dental emergencies, and the progression of any chronic conditions that existed before launch. The crew must have the medical training and the equipment to manage any of these without emergency rescue, because emergency rescue is impossible on any relevant time scale. The return journey adds its own specific psychological stressor. The re-entry into microgravity after 500 days at 38% gravity. The crew must manage their physiological adaptation to zero gravity in the return spacecraft, execute a 7-month return transit in a smaller and less comfortable volume than the Mars habitat, and maintain mission-critical cognitive function throughout the return transit despite the radiation history of the mission. The last 7 months of the return transit, with Earth visible but not yet reachable, is psychologically the hardest part of the mission for most astronaut psychology researchers who have modeled it. Let me now describe the specific scenario of Earth re-entry, because it is the final physical challenge and the one that directly tests the cardiovascular deconditioning I described at the opening. After the trans-Earth transit, the spacecraft enters Earth's atmosphere at approximately 11 kilometers per second relative to the atmosphere. The deceleration from entry to landing produces approximately 3 to 4 Earth gravities for a period of 8 to 12 minutes, depending on the entry trajectory and the specific vehicle design. This is a standard feature of Earth re-entry vehicles and has been managed successfully for ISS astronauts returning after 6 months in microgravity. The challenge for a Mars return crew is the magnitude of their cardiovascular deconditioning. An ISS astronaut returning from 6 months in microgravity has a left ventricular mass that is approximately 10% below normal and a reduced blood volume. These individuals manage the 3 to 4G entry loads with appropriate countermeasures: fluid loading before entry to restore blood volume, anti-G suits to prevent blood pooling in the legs, and mission control monitoring for cardiovascular compromise. A Mars return crew has been in reduced gravity for a total of approximately 21 months out of a 30-month mission. Their cardiovascular system has had 2 periods of partial recovery in Martian gravity, interrupted by 2 periods of zero gravity adaptation. The net cardiovascular deconditioning at re-entry is substantially greater than for an ISS mission. The specific risk is loss of consciousness during the 3 to 4G deceleration, which would not be fatal if the spacecraft is operating autonomously, but represents a failure of the physiological capacity that the mission requires its crew to maintain. Countermeasures for re-entry cardiovascular stress are the same as for ISS returns, but must be effective over a much larger deconditioning deficit. Whether fluid loading and anti-G suits that are effective after 6 months in microgravity are equally effective after 21 months in below-Earth gravity is unknown. It is one of the parameters that cannot be tested except by doing the mission. The landing itself, if direct Earth surface landing is used, exposes the crew to 1 Earth gravity for the first time in 30 months. This is the moment when the full weight of the mission's physiological legacy is felt. Every bone that has lost mineral density over 30 months must now support the crew member's weight against full Earth gravity. Every muscle that has atrophied must now work against full gravitational loading. Every cardiovascular system that has adapted to zero and partial gravity must now maintain perfusion pressure against the full hydrostatic column of blood in the upright human body. ISS astronauts who land in Kazakhstan after 6 months in microgravity typically cannot walk unassisted for hours to days after landing. They require physical rehabilitation lasting weeks to months before they regain full functional capacity. A Mars return crew with a substantially larger physiological deficit would require substantially longer rehabilitation and would have a higher risk of complications, including fractures from falls, cardiovascular events from orthostatic intolerance, and slower recovery of cognitive function. None of these complications is necessarily fatal. All of them are manageable with appropriate medical support, but they represent the final expression of the accumulated physiological cost of the mission, and their severity is unknown, because no human being has yet experienced anything like the total physiological loading of a Mars round trip. Let me now put the physiological challenges in historical and programmatic context, because the data we have comes from a specific body of research that has been accumulating since the first human spaceflight, and understanding its limitations is essential for understanding how confident we can be about predicting the Mars mission outcome. Human beings have been flying in space since 1961. The total accumulated human spaceflight experience as of 2024 is approximately 600 person years in orbit. The longest single spaceflight was Valery Polyakov's 438-day mission on Mir in 1994 and 1995. The second longest was Sergei Avdeyev's 380 days on Mir in 1998 and 1999. The longest American spaceflight was Mark Vande Hey's 355 days on ISS in 2021 and 2022. These long-duration missions provide the most relevant data for predicting Mars mission outcomes. Polyakov's 438-day mission, in particular, is often cited as evidence that humans can survive the duration of a transit to Mars in microgravity. After landing, Polyakov reportedly refused a stretcher and walked from the Soyuz capsule, demonstrating that his physical capacity, while diminished, was sufficient for unassisted ambulation after more than 14 months in microgravity. But Polyakov's mission was not a Mars mission in several critical respects. He was in low Earth orbit, protected by Earth's magnetosphere from most galactic cosmic ray exposure. His radiation dose during 438 days on Mir was approximately 430 millisieverts, comparable to the transit dose for a Mars mission, but without the surface dose or the return transit dose. He returned directly to Earth's full gravity, without needing to function in partial gravity first, and without needing to execute a complex sequence of propulsive maneuvers. He was debriefed within hours of landing by Earth-based medical teams with access to all required resources. The data from Polyakov and other long-duration astronauts tells us about the individual components of the Mars physiological challenge: the cardiovascular deconditioning, the bone and muscle loss, the SANS risk. What it cannot tell us is how these components interact with each other when they are all operating simultaneously at larger magnitudes in the Martian gravity environment, with the radiation loading of the full mission and without the option of Earth-level medical support. The twin study performed by NASA on astronauts Scott and Mark Kelly provides the most genomically detailed data on spaceflight effects. Scott Kelly spent 340 days on ISS in 2015 and 2016, while his identical twin brother, Mark, a former astronaut, remained on Earth as a control. The study examined genomics, telomere length, gene expression, the microbiome, cognition, and many other endpoints. Several findings from the twin study are relevant to a Mars mission. Scott Kelly's telomere length increased during spaceflight, which was unexpected, and then rapidly returned to near baseline after landing with some accelerated shortening, his gut microbiome composition changed significantly during space flight. His gene expression patterns showed changes in thousands of genes, including inflammatory pathways and DNA repair pathways. His cognitive performance on standardized tests showed some decline during and after the mission, although not dramatically. The twin study demonstrates that spaceflight affects human biology at the most fundamental levels of genomic regulation and microbial ecology in ways that were not fully appreciated before the study. It does not provide a complete prediction of what a Mars mission would do, because the Scott Kelly mission was in low Earth orbit at partial shielding for 340 days without the Martian surface component or the radiation loading of a full Mars mission. The research program for crewed Mars missions requires specific studies that have not yet been done. Studies of human physiology in partial gravity environments other than zero gravity. Studies of the combined effect of radiation and microgravity on cognition over durations of more than a year. Studies of autonomous propellant production on the Martian surface at mission scale. And studies of closed-loop life support systems over multi-year durations. None of these studies can be done without either going to Mars or creating more sophisticated analog environments than any that currently exist. This is the research program gap that makes the return from Mars uncertain in a fundamental way. We are not in a position where we have done all the studies and know the answers. We are in a position where many of the most important questions about the mission's physiological risks can only be answered by doing the mission. Let me also describe the specific challenge of the microbiome and immune function, because it is one of the least discussed aspects of long-duration spaceflight and is particularly relevant for a mission that must be medically self-sufficient. The human gut microbiome contains approximately 38 trillion bacteria, roughly equal to the number of human cells in the body. These bacteria perform essential metabolic functions. They synthesize certain vitamins, metabolize complex carbohydrates that human enzymes cannot digest, train the immune system, and produce neurotransmitter precursors that affect mood and cognition. The specific composition of the microbiome is shaped by diet, environmental exposures, and the immune system. It is not static, but is in continuous dynamic equilibrium with the host physiology and environment. In the closed, sterile environment of a spacecraft, the microbiome faces a radical change in environmental inputs. The food is freeze-dried and packaged, lacking the diversity of fresh food that shapes the terrestrial microbiome. The cabin environment contains only the microorganisms that the crew brought with them, which are continuously recirculated and which cannot be replenished from the terrestrial environment. The physical and chemical properties of the cabin air are different from outdoor air on Earth in ways that affect microbial survival and growth. Studies of ISS crew microbiomes show measurable changes in microbial composition during spaceflight. Some commensal species decrease and some potentially pathogenic species increase. The immune system, which normally maintains this balance through continuous surveillance and selective tolerance, must manage the changed microbial landscape in an environment that also includes elevated radiation, sleep disruption, and psychological stress, all of which individually impair immune function. The specific risk for a Mars mission is twofold. First, an immune system operating under the combined stressors of radiation, sleep disruption, and stress over 30 months may fail to adequately control opportunistic pathogens. An otherwise minor infection could become serious in the absence of Earth-level medical support. Second, the antibiotic resistance profile of microorganisms aboard a spacecraft evolves over time as selective pressure from antimicrobial surfaces and limited antibiotic diversity shapes the microbial ecology of the cabin. Strains that are resistant to the antibiotics carried by the mission may emerge. Managing medical emergencies including infections, on a Mars mission requires the crew to carry a specific formulary of medications, have the medical knowledge to use them appropriately, and have diagnostic capabilities sufficient to identify the specific pathogen and its resistance profile. These capabilities can be designed into the mission, but they cannot be equivalent to a fully equipped hospital with access to a specialist for every possible medical scenario. The Apollo 13 experience is instructive. A life-threatening emergency was managed by combining the expertise of the crew, who were trained pilots and engineers with astronaut medical training, and the resources of an enormous ground support team with real-time communication. On Mars, the equivalent scenario has neither real-time ground support nor the resources of mission control accessible within a response time that can change the outcome of an acute emergency. Let me now describe the specific challenge of the life support system, because it is the infrastructure on which everything else depends, and its failure is the ultimate barrier to return. A crewed Mars habitat must maintain breathable air, potable water, and food supply for the crew for 500 days on the surface. The life support system must recycle oxygen from the crew's exhaled carbon dioxide, recycle water from the crew's urine, sweat, and exhaled humidity, and manage trace contaminants in the cabin atmosphere. The ISS life support system performs all these functions with a regeneration efficiency that has improved over the decades of ISS operation. The ISS life support system still requires regular resupply of consumables that cannot be fully recycled: food, certain chemicals, replacement parts for equipment that wears out. The resupply frequency for ISS is approximately every 2 to 6 months. On Mars, resupply from Earth takes a minimum of 8 months transit time and can only be executed during the approximately 2-month launch window that opens every 26 months. The consumable budget for a Mars mission must account for the possibility of a resupply mission being delayed or failing, which means carrying sufficient reserves for the full mission duration with no resupply. The specific failure modes that could make the Mars habitat uninhabitable include failure of the oxygen production system, failure of the water recycling system, structural breach of the habitat by micrometeorite impact or seal failure, catastrophic dust storm that blocks solar panels and depletes power reserves, and failure of the carbon dioxide removal system. Each of these failure modes must be protected against with backup systems and adequate reserves. The probability that all required systems function for 500 days on Mars without any resupply or significant outside maintenance cannot be determined with confidence from Earth-based testing. The interaction between life support reliability and the return from Mars is specific. If the life support fails before the return launch window opens, the crew must evacuate to the Mars ascent vehicle and attempt to launch outside the optimal window, accepting the delta V penalty and the increased propellant requirement. If the ascent vehicle propellant is not full because the production timeline was delayed, the crew may not have enough propellant to execute both the ascent and the trans-Earth injection. The potential interaction between life support failure and propellant availability is a specific and serious risk that mission planners must address with system redundancy that adds mass and complexity. All of these specific technical details, the microbiome changes, the immune function concerns, the life support reliability, and the propellant production dependency are part of what I mean when I say the return from Mars is genuinely uncertain. The individual pieces are understood. The combination is not fully understood, has never been tested at scale, and cannot be tested without a Mars mission. The most honest summary of the situation is this. Based on everything we know about human physiology, orbital mechanics, and Mars surface conditions, a crewed Mars round trip is within the range of what physics and biology might permit. It is not within the range of what we can confidently predict will succeed. The gap between those two statements is where the real difficulty lies. that deserves its own careful treatment because it is less well known than bone loss or radiation, but has been identified in the last decade as a potentially mission-limiting risk for long-duration spaceflight. Spaceflight-associated neuroocular syndrome, or SANS. SANS was identified as a clinical entity in 2011 when NASA's Human Research Program compiled data from multiple long-duration ISS astronauts who showed structural changes in their eyes that were not present before flight. The changes included flattening of the posterior portion of the eyeball, called globe flattening, swelling of the optic disc, the point where the optic nerve meets the retina, folds in the choroid, the vascular layer behind the retina, and, in some cases, choroidal folds extending into the macula, the central portion of the retina responsible for high-resolution vision. These structural changes are associated with visual impairment. Approximately 40% of astronauts who fly long-duration missions on ISS report some degree of vision change during or after flight. Some astronauts show persistent vision changes that do not fully resolve after return to Earth. The specific changes vary between individuals, suggesting individual differences in susceptibility. The mechanism is believed to be elevated intracranial pressure from the cephalad fluid shift in microgravity. When the body's fluid redistributes toward the head in zero gravity, cerebrospinal fluid pressure increases. The optic nerve sheath, which contains cerebrospinal fluid, transmits this elevated pressure to the eye, causing the structural changes observed. The choroidal folds and optic disc swelling are the direct mechanical consequence of elevated pressure behind the eye. For a Mars mission, SANS is relevant in two specific ways. First, during the transit periods, when the crew is in microgravity, the cerebrospinal fluid pressure is elevated and SANS may progress. On Mars, with 38% gravity, the cephalad fluid shift is reduced but not eliminated. 38% gravity is enough to restore some of the normal hydrostatic gradient, but not the full gradient present at Earth's surface. The rate of SANS progression in partial gravity is unknown. Second, if SANS causes significant visual impairment, it directly impairs the ability of crew members to read instrument displays, perform precision operations during ascent and rendezvous, and conduct the EVAs required for surface operations and vehicle maintenance. Vision is operationally critical in a way that can be partially compensated for by updated prescriptions, but the structural changes in the eye cannot be reversed by corrective lenses. SANS is still poorly understood. The specific risk factors that predict which individuals will develop severe SANS are not established. The interventions that might prevent or treat SANS in space are experimental. Lower body negative pressure devices that counteract the fluid shift have shown some promise, but their effectiveness over long missions is not established. Intracranial pressure monitoring via implanted sensors has been proposed, but is invasive and not yet applied routinely to astronauts. For the return from Mars, SANS adds a specific operational risk that is separate from the radiation-related cognitive effects and the cardiovascular deconditioning. An astronaut with significantly impaired vision at the time of the Mars ascent, rendezvous, and trans-Earth injection burns is a mission risk that must be accounted for in the mission design. The probability of significant SANS in any given crew member after a 30-month mission is unknown. I want to step back now and describe what all these specific constraints add up to, because the full picture is more than the sum of the parts. You arrive on Mars after a 210-day transit with 7 to 10% of your femoral neckbone mineral density gone, 15 to 20% of your lower body muscle mass reduced, cardiovascular capacity adapted to zero gravity, galactic cosmic ray dose of 300 millisieverts on your way to exceeding your career limit, and early cognitive effects from the HZE component of that dose. Your eyes may already show the early structural changes of SANS. you are adapted to zero gravity and now must function in 38% gravity. For the next 500 days, you work on Mars. The gravity partially restores your bone and muscle loading. Your cardiovascular system partially readapts. But you continue to accumulate radiation dose at approximately 100 millisieverts per year. Your SANS either stabilizes or progresses. Your psychological reserves deplete as the mission extends. The propellant plant operates autonomously and you monitor it through automated telemetry. After 500 days, you are physically diminished compared to arrival. Your total radiation dose is approaching 500 millisieverts. Your bone mineral density may be partially restored by the Martian gravity, but is almost certainly still below pre-flight levels. Your muscle mass has partially recovered. Your cardiovascular system has partially readapted to gravity. Now you re-enter microgravity for the return transit. All the deconditioning processes begin again. For 7 months, your skeleton is unloaded. Your muscle mass declines. Your cardiovascular system readapts to zero gravity. The radiation dose climbs toward 600 to 700 millisieverts. When you finally enter Earth's atmosphere, your body has been in reduced or zero gravity for 21 of the last 30 months. Your bone mineral density is at the lowest point of the entire mission. Your cardiovascular system must manage 3 to 4 G of deceleration. If you survive re-entry, you land in full Earth gravity for the first time in 30 months. Recovery will take years. This is the complete physical picture of the return from Mars. Not a single obstacle, but an accumulation of obstacles, each compounding the others, each adding its specific physiological cost to the crew that must navigate them all simultaneously. The return from Mars is not just difficult. It is at the edge of what we know human beings can endure. I have tried in this video to give you the honest physics, the specific numbers, the specific mechanisms, the specific unknowns, not to argue that the mission should not be done, but to be clear about what it requires. The engineers and scientists working on crewed Mars missions know this material. The question of whether the mission will be done and whether it should be done depends on values that the physics cannot determine. The physics can only tell you clearly and precisely what the constraints are. Let me now address the one technological improvement that is most often cited as the solution to the return problem: nuclear thermal propulsion. Nuclear thermal propulsion uses a nuclear fission reactor to heat a propellant, typically hydrogen, to extremely high temperatures, which then expands through a nozzle to produce thrust. The specific impulse of a nuclear thermal rocket, which is the measure of propellant efficiency equivalent to fuel economy in a car, is approximately 800 to 900 seconds. Chemical rockets achieve approximately 450 seconds for the best engines. The nearly doubled specific impulse means that nuclear thermal propulsion can achieve the same velocity change as a chemical rocket with roughly half the propellant mass, or the same propellant mass achieves a much greater velocity change. The practical consequence for a Mars mission is significant. A nuclear thermal spacecraft could reach Mars in approximately 100 to 130 days, rather than 180 to 210 days. The shorter transit reduces the transit radiation dose from approximately 300 millisieverts to approximately 170 millisieverts. A meaningful reduction. The shorter transit also reduces the microgravity deconditioning period, improving the crew's physical condition at arrival on Mars. NASA has been developing nuclear thermal propulsion technology intermittently for decades. The NERVA program, nuclear engine for rocket vehicle application, was active in the 1960s and early 1970s and demonstrated nuclear thermal rocket engine performance at the component level, achieving specific impulse values above 825 seconds. The program was canceled in 1972 for budgetary reasons and political priorities, not because of technical failures. Recent programs, including the Draco demonstration mission planned for the late 2020s as a joint effort between DARPA and NASA, aim to demonstrate nuclear thermal propulsion in space. Nuclear thermal propulsion is real physics, demonstrated technology at the component level, and a credible path to shorter Mars transit times. But it does not eliminate the return problem, it reduces it. Even with a 100-day transit, the crew still arrives on Mars with measurable bone and muscle loss from the transit period in microgravity, though less than with a chemical rocket transit. The surface stay of 500 days is unchanged because it is determined by the orbital mechanics of the launch window, not by the transit duration. The radiation dose accumulated on the Martian surface is unchanged, approximately 100 millisieverts over 500 days. The return transit, another 100 days in microgravity, adds another approximately 170 millisieverts. The total mission dose with nuclear thermal propulsion, approximately 550 millisieverts, is marginally lower than with chemical propulsion, approximately 700 millisieverts, and still approaches the NASA career limit. The propellant production requirement on Mars is unchanged because it is determined by the delta V required for the ascent and trans-Earth injection, not by the transit propulsion. The propellant plant must still produce approximately 1,200 tons of methane and liquid oxygen for a Starship-class vehicle. The 500-day surface stay constraint is unchanged. The orbital mechanics constraints are unchanged. Nuclear thermal propulsion makes the Mars round trip somewhat more physically manageable by reducing the transit periods. It does not change the fundamental nature of the challenge, which is the compounding of 5 barriers over a 30-month mission with no abort option and no rescue capability. A further technological improvement that is sometimes discussed is artificial gravity through rotation during the transit periods. If the spacecraft spins during the transit, centrifugal force provides a simulated gravitational environment for the crew. At 2 revolutions per minute with a habitation module radius of approximately 225 meters, the centrifugal force at the outermost point would equal 1 Earth gravity. A rotating spacecraft of this scale is a significant engineering challenge, but is not physically impossible. Existing space structures, including the ISS, are large, but the ISS has a radius of approximately 51 meters, far short of the 225 meters needed for 2 revolutions per minute without Coriolis sickness. A tethered system in which the crew module and a counterweight are connected by a long tether and spin around a common center of mass could achieve the required radius with less structural mass, but the tether and spin up and spin down mechanics add complexity. If artificial gravity is provided during the transit periods, the bone loss and cardiovascular deconditioning from the transit are largely eliminated. The total physiological deficit at arrival on Mars is much smaller. The return transit, if also in artificial gravity, avoids the additional deconditioning that the return transit currently adds. The crew would arrive home in a physiological state much closer to that of an ISS astronaut returning from 6 months, rather than a crew member returning from 30 months of varied gravity environments. Artificial gravity during the transit does not address the radiation problem, the psychological isolation problem, the propellant production problem, or the orbital mechanics constraints. It addresses one dimension of the physiological challenge, and a significant one: the musculoskeletal and cardiovascular deconditioning that currently represents the largest single physiological risk for the return trip. The combination of nuclear thermal propulsion, reducing transit time and radiation dose, with artificial gravity during the transit, eliminating most of the musculoskeletal and cardiovascular deconditioning, would significantly improve the return scenario. The crew would arrive on Mars in near normal physiological condition. The radiation accumulated during the surface stay would be the dominant dose, approximately 100 millisieverts in 500 days. The return transit dose would be reduced by the shorter transit time and would not add musculoskeletal deconditioning if artificial gravity is maintained. This combination does not exist. Nuclear thermal propulsion has not been demonstrated in space. Artificial gravity through rotation has not been demonstrated on any crewed spacecraft. Both are credible technologies based on known physics. Neither has been developed to the point of being available for a crewed Mars mission in any near-term planning horizon. The point of going through these potential mitigations is not to suggest that the problem is intractable. It is to be honest about where the technology actually is versus where it needs to be, and to identify specifically which capabilities would change the return scenario most significantly. The two most important missing capabilities for the return from Mars are nuclear thermal propulsion and artificial gravity during transit. Both are achievable in principle. Neither is available now. The gap between current capabilities and required capabilities is not a reason to give up on the mission. It is a reason to be honest about the timescale and the technical development required. A crewed Mars round trip with current technology is at the boundary of what the human body can endure. A crewed Mars round trip with nuclear thermal propulsion and artificial gravity transit is more safely within that boundary, though still at the frontier of human endurance. The specific development path from current capabilities to mission-capable technology is known. What it requires is sustained investment, political will, and sufficient time to develop and demonstrate the relevant technologies before committing humans to the mission. The early European explorers who crossed the Atlantic did not have reliable return routes established before they departed. Ferdinand Magellan, whose expedition became the first to circumnavigate the Earth, did not survive the journey himself, dying in the Philippines in 1521. Of the 5 ships and approximately 270 men who began the expedition, only 1 ship and 18 men completed the circumnavigation. The expedition was counted a success because the knowledge and the trade routes were obtained, not because everyone came back. The expeditions to Antarctica in the early 20th century accepted risk of non-return as the cost of exploration at the frontier of the accessible world. Robert Falcon Scott and his 4 companions died on the return from the South Pole in March 1912. Ernest Shackleton's Endurance expedition lost its ship but saved all 27 crew members through extraordinary leadership and fortune. These expeditions are celebrated not because they were without cost, but because what was gained justified what was risked. The Apollo program accepted a specific risk of fatality that would be unacceptable by contemporary standards. NASA's internal estimates during Apollo were that there was approximately a 15% chance of crew loss over the entire Apollo program. The first crew was, in fact, lost. Gus Grissom, Ed White, and Roger Chaffee died in the Apollo 1 fire on the launch pad in January 1967. The Apollo 13 crew survived the mission only because of specific contingencies that happened to be available at the specific moment of the failure. What distinguishes these historical precedents from a crewed Mars mission is not the risk level, it is the nature of the risk, the timescale, and the ability to respond to problems. For Antarctic expeditions and ocean voyages, the fundamental physical challenges were understood well enough that the risks could be characterized in advance. The cold would be this cold. The distance would be this far. The food would last this many days. The uncertainty was in the execution, not in the nature of the environment. For a Mars mission, some of the fundamental physical challenges cannot be characterized in advance with confidence because they involve biological responses to conditions that have never been sustained for the required duration. We do not know exactly how the human body responds to 30 months in the specific combination of environments that a Mars mission involves. We do not know because no human being has ever experienced that combination, and the individual components that we do have data on are not fully sufficient to predict the combined response. This is why the return from Mars is different from the return from Antarctica or from the Moon. It is not just that it is harder, it is that the specific nature of the uncertainty is different. The uncertainty is not primarily about engineering, it is about biology. And biology, unlike engineering, cannot be fully tested in the laboratory before the mission. The full test is the mission itself. I want to be clear about what this means for the decision to fly a crewed Mars mission. I am not arguing that it should not be done. The scientific value of a crewed Mars mission is extraordinary. The symbolic value of the first human presence on another planet is incalculable. The potential to establish a permanent human presence on Mars, with all that implies for the long-term future of our species, is real and important. I am arguing that the decision should be made with full information about what the physics and biology require, not with the optimism-biased narrative that characterizes most public communication about Mars. The crew of the first Mars mission will be asked to accept risks that no previous human beings have accepted over a timescale that no previous mission has required, with physiological consequences that cannot be fully predicted. They deserve to have those risks characterized honestly. And the broader public, whose resources and whose support are required to make the mission possible, deserves to understand what they are supporting, not a bold but manageable engineering challenge. A genuinely uncertain venture that requires the human body to do things it has never been asked to do over timescales it has never been tested at, with no ability to rescue the crew if the biological or engineering systems fail in ways that current medicine and engineering cannot prevent. That is the honest physics of the return from Mars. It is more demanding, more uncertain, and more important to understand clearly than any narrative about the mission as an exciting but achievable engineering challenge has so far acknowledged. If any of what I have described changed how you think about crewed Mars missions, the specific biological costs of the transit, the radiation effects, the orbital mechanics constraints, the propellant production dependency, or the compounding of all of them, tell me what in the comments. Tell me whether you think the mission should proceed given these risks and why. Tell me whether a one-way mission changes your assessment. And subscribe if you want to keep going into the places where the physics of human existence in space meets the honest biological and engineering limits of what is achievable. The honest picture is this: a Mars round trip is physically possible in principle, but is at the boundary of human physiological capacity in ways that we do not fully understand. Every specific factor I have described, the bone loss, the muscle loss, the radiation dose and its cognitive effects, the propellant requirement, the launch window constraint, the psychological demands of isolation, and the re-entry cardiovascular stress, is individually manageable within large uncertainty bounds. Some of them have partial mitigations. Bone loss can be reduced with better exercise equipment and pharmacological agents. Radiation can be reduced with shorter transit times using nuclear thermal propulsion. Propellant production can be scaled up with sufficient investment in precursor missions. Each barrier can be partially addressed. The problem is the combination. The combination of all these factors acting on the same crew over the same mission pushes the total physiological and operational challenge to a level that has never been tested and cannot be tested except by doing it. You cannot test the combined effect of 7 months of microgravity, 500 days of partial gravity, and 7 months more of microgravity on a human body in any terrestrial simulation. You cannot test the combined effect of the mission's total radiation dose on human cognition without exposing humans to that dose. You cannot test the reliability of an autonomous propellant plant in the Martian environment without putting one on Mars. This is what it means to say the mission is at the boundary of the achievable, not impossible by physics, not impossible in principle, but at the frontier of what we know in multiple independent ways simultaneously. The compounding of uncertainties across all these dimensions is what makes the return from Mars genuinely uncertain rather than merely technically challenging. Let me now address the specific proposal that has been advanced by several serious thinkers, including the founding president of the Mars Society, Robert Zubrin, and various members of the Mars planning community: the one-way mission. The argument is that if the return is so difficult, perhaps the first Mars missions should be one-way, with the crew landing and remaining permanently with resupply from Earth but without a return vehicle. The one-way mission argument has a specific logic to it that deserves honest examination. It eliminates the propellant production requirement for return. It eliminates the return transit and the additional radiation dose, bone loss, and psychological burden that the return transit represents. It dramatically simplifies the mission architecture and reduces the mass that must be landed on Mars. The one-way mission is not inherently suicidal. A permanent Mars base supplied with regular cargo missions could, in principle, support an indefinitely growing human presence on Mars. The crew would age and eventually die on Mars, as people die on Earth, rather than returning home after a defined mission. Whether this is ethically acceptable, whether it is possible to find volunteers who genuinely understand and accept this commitment, and whether the resupply infrastructure required to sustain a permanent presence can be made reliable enough are real questions. The specific physical constraints of the return are not reasons to prefer a one-way mission on grounds of safety. A one-way mission crew still faces the radiation, the partial gravity, the psychological isolation, and the propellant and life support dependencies, just without the requirement to reverse them for a return trip. They face these challenges for the rest of their lives rather than for a defined mission period. Whether this is better or worse depends on values that physics cannot adjudicate. What the physics can say is this: every one of the barriers I have described for the return journey is real. The orbital mechanics are fixed. The radiation environment will not change. The biology of the human body has been shaped by billions of years of evolution and will not be reprogrammed by the decade-scale technology development programs that precede the first crewed Mars mission. The propellant production requirement follows from the delta V required and the Tsiolkovsky rocket equation. These constraints define the problem precisely, and any Mars mission architecture must reckon with them exactly as they are. The engineers and mission planners who are working on crewed Mars missions know all of this. The technical literature on Mars mission medicine, propulsion, and mission architecture is extensive and rigorous. The challenges are not hidden or ignored in the professional community. They are sometimes understated in public communications, perhaps because the goal of maintaining public and political support for the program requires an optimistic tone. Perhaps because the full picture is difficult to convey without the technical background required to appreciate it. What I have tried to do in this video is give you that full picture, not just the individual challenges, but the way they combine, not just the engineering problems, but the biological ones, not just the outbound journey, but the return, with specific numbers and specific physical mechanisms. If the mission is going to be done, and there are good reasons why it might be, it should be done with full understanding of what it requires. The physics of the return from Mars is not a problem to be solved later. It is a set of constraints that must be addressed before the first crew commits to landing. The propellant must be in the tanks before the lander separates from the Earth return vehicle. The crew must be physically and cognitively capable before they launch from the Martian surface. The launch window is a hard deadline that the orbital mechanics impose without exception. These are the constraints that define what it means to try to come back from Mars. They are severe, they are well understood at the level of individual components, and they are impossible to fully test without doing the mission. That is the honest physics of the situation. It is more interesting and more demanding than any popular narrative about Mars settlement has fully acknowledged. If this changed, how you think about the specific physical challenges of a Mars round trip, if the combination of radiation, physiology, propellant production, orbital mechanics, and re-entry stress presents a picture more complex than the standard narrative of an engineering challenge to be solved, tell me in the comments. Tell me whether you think the biological barriers are more or less tractable than the propellant production barriers. Tell me whether a one-way mission to Mars with the explicit intention of permanent settlement and no return changes the ethical and physical calculus in a way you find compelling. And subscribe if you want to keep going into the places where the physics of human space exploration meets the honest limits of what the human body and the laws of the solar system will actually allow. The 12 principles in my book are about this exact kind of clear-eyed engagement with what reality allows and what it demands. Ready to change how you see the world? Get your copy of 12 Principles for Understanding the Fabric of Reality at realityprinciples.com